Hello everyone and welcome to another video on our own devices. I'm Jean Messier and today we are having a look at a rocket. And not just any rocket, a very Canadian rocket that I happen to have a slight personal connection to. This is a Canadian rocket vehicle, or CRV-7. This is a 70mm or 2.75-inch unguided air-to-ground rocket munition developed by Bristol Aerospace Ltd in the early 1970s for use aboard Canadian and other NATO aircraft. Now, Bristol Aerospace Ltd, today Magellan Aerospace Ltd, happens to be headquartered in my hometown of Winnipeg, Manitoba. And when I was studying engineering, quite a few years ago now, I worked as a summer student for one summer at the plant just north of Winnipeg that produces CRV-7. So I got to see how these were designed and manufactured. So, without any further ado, let's dive right in and let me show you where these came from and how they work. Now, air-launched rocket weapons actually have a surprisingly long history. As early as 1916, various Entente aircraft were fitted with nuclear rockets, invented by French Army Lieutenant Yves Le Prieur for use against German hydrogen-filled observation balloons and zeppelins. These were effectively giant black powder fireworks, complete with long wooden stabilizing sticks launched from an aircraft's interplane struts. The idea was that, unlike a regular machine gun bullet, the burning rocket would actually ignite the hydrogen as it passed through the balloon envelope or Zeppelin gas bag. However, the Prieur rockets proved extremely inaccurate and short-ranged, and by the end of the war had been largely replaced by the far more effective Brock, Pomeroy, and Buckingham incendiary and explosive machine gun ammunition. Air-launched rockets became even more common during the Second World War, both for air-to-air and air-to-ground use. Some more common examples include the British 3-inch or 60-pound rocket projectile, or RP-3, the Soviet RS-82 and RS-132, the American Tiny Tim and high-velocity aircraft rocket, or HVAR, aka the Holy Moses, and the German R-4M Huracan and Werfergranate 21. The latter was derived from the projectile from the ground-based Nebelwerfer 42, and if you want to learn more about German World War II rocket launchers, please check out my previous videos on the 30cm Raketenwerfer 56 and the Raketenwerfer 43, links in the description. Many of these rockets remained in service well after the war, with the British RP-3 being carried aboard jets like the Hawker Hunter until 1967, when it was replaced by the French 37mm and 100mm SNEB, or Matra rocket, and then the 2-inch RP. The American HVAR also remained in service well into the 1970s, being carried by aircraft like the Grumman Panther and Lockheed P-80 Shooting Star in Korea and the Douglas A-1 Skyraider in Vietnam. It also served alongside the 70mm or 2.75-inch Mark 40 Folding Fin Aerial Rocket, or FFAR, aka the Mighty Mouse, and the 5-inch Folding Fin Aircraft Rocket, or Zuni. Eventually, these were all supplanted by the 70mm or 2.75-inch Hydra 70, which is still in service in 25 countries. Now, while mechanically post-war rockets were very similar to their Second World War forebears, they did benefit enormously from advancements in rocket propellant composition. Now, the earlier World War II era rockets mainly used what are known as double-based propellants, which are largely based on nitrocellulose, nitroglycerin, and various other binders and additives. Perhaps the best known of these compositions was cordite, composed of 58% nitroglycerin, 37% nitrocellulose, and 5% petroleum jelly dissolved in acetone and extruded into spaghetti-like sticks. This is notably used as a propellant in British small arms and artillery ammunition, as well as rockets like the RP-3. Later formulations like cordite SC and cordite N included additives like ethyl centralite and nitroguanidine to slow the combustion rate and reduce flame temperature and muzzle flash. As the latter additive is a nitro compound, these compositions were typically known as triple-base propellants. These were cast into fuel grains in one of two ways. In the Ball process, propellant was ground up into small granules which were packed into the rocket motor case. The case was then evacuated and a liquid plasticizer introduced, which would fill the interstices between the granules and cure, forming a solid grain. An alternative method was the plastisol process, in which the propellant was mixed with a solvent to form a slurry that was poured into the casing and allowed to solidify. Now, ballastite, developed by the Hercules Powder Company and used in the HVAR and Tiny Tim, was composed of 51.5% nitrocellulose, 43% nitroglycerin, 3.5% diethyl phthalate, 1.25% potassium sulfate, 1% ethyl centralite, and 0.2% carbon black. This composition gave ballastite motors a higher specific impulse of 200 seconds compared to around 180 seconds for other propellants like cordite. They also developed an innovative way of casting the blocks or grains of solid propellant. See, up until this point, most rocket motors had a solid cylindrical grain which burned from one end to the other. Now, since the burning rate and thus the chamber pressure and thrust of solid rocket motors is directly proportional to the total area of fuel burning at any given time, this produced fairly mediocre performance. Not only that, but it also subjected the motor case to an extreme amount of thermal stress as the very small but very hot flame front traveled from one end to the other. The grains of the HVAR and tiny tin, by contrast, featured a central cruciform channel or port with the propellant burning from the inside out. This not only allowed a larger surface area of propellant to burn all at once, greatly increasing combustion rate and performance, but also protected the casing from thermal stress, as the flame front did not reach the casing until just before motor burnout. As for the cruciform cross-section, this helped keep the combustion rate, and thus the thrust, consistent throughout the burn, since as this shape erodes, the total exposed surface area inside the grain remains relatively constant. This configuration is now effectively standard for most solid rocket motors up to the SRBs used by the Space Shuttle and the Space Launch System, or SLS. Yet despite these improvements, traditional double and triple base propellants remained highly unstable, shock-sensitive, and prone to degradation at high temperatures. This is why post-war, most manufacturers switched over to so-called composite propellants, composed of a solid oxidizer, typically ammonium perchlorate, mixed with some sort of elastomer that serves as both binder and fuel. Powdered aluminum and magnesium is often also added to increase specific impulse. Now, composite propellants had been made using nitrocellulose double-base compositions as the binder, but in 1942, Caltech engineer Jack Parsons, later one of the founders of the Jet Propulsion Laboratory, or JPL, developed a new, more stable kind of composite fuel composed of ammonium perchlorate mixed with asphalt as part of research into rocket-assisted takeoff, or RATO motors, for aircraft. His colleague Charles Bartley later experimented with replacing the rather gooey asphalt with various more solid elastomers, including polyvinyl chloride, polyvinyl acetate, neoprene, and styrene butadiene rubber. Further research by companies like Atlantic Research Corporation, Thiokol, and Aerojet eventually produced the most common solid rocket propellant composition in use today, based on hydroxyl-terminated polybutadiene, or HTPB. And all this finally brings us to the CRV-7, which grew out of rocket propellant research conducted at the Canadian Armaments Research and Development Establishment, or CARDI, in Valcartier, Quebec. In the late 1950s, CARDI was studying anti-ballistic missile, or ABM systems, and created a small rocket called the Propulsion Test Vehicle, or PTV, to test various solid propellant compositions. When the ABM program was cancelled, the PTV was developed into the highly successful Black Brant sounding rocket, which is still manufactured by Bristol Magellan Aerospace today, and widely used by multiple countries to conduct high-altitude research. If you want to learn more about the history of sounding rockets, please check out the lecture I gave on the subject and the video I wrote for Today I Found Out on the 1995 Norwegian rocket incident when a Black Brant nearly caused World War III. Links in the description. Now, in the early 1970s, CARDI and Bristol, under the direction of engineer José Ferrayel, decided to use the same high-performance solid propellant developed for the PTV and Black Brant to create a more powerful version of the American 2.75-inch Hydra 70 unguided rocket to equip RCAF CF-104 Starfighter strike aircraft based in Western Europe. The goal was to produce a rocket with a longer range, flatter trajectory, and greater kinetic energy that could penetrate the roofs of hardened Warsaw-packed aircraft shelters. The CRV-7 first entered production in 1973 and was based around the C-14 or RLU-5001/B rocket motor. This had a burn time of 2.2 seconds and a total impulse of 10.3 kilonewton seconds, or 2,320 pound-force seconds, giving it a burnout velocity of 1,000 meters or 3,280 feet per second, and a maximum effective range of 4,000 meters or 13,000 feet. By comparison, the Hydra 70, which uses the Mark 66 rocket motor, has a burnout velocity of 739 meters or 2,425 feet per second and an effective range of 3,000 meters or 9,840 feet. Right, so that is a lot of background information, and I think it's about time we had a look at the hardware I have here and some of the more interesting design features of the CRV-7. Now, unfortunately, this is an inert example, so there's no propellant inside. I can't show you the configuration of the propellant grain. However, there's still plenty to look at. So, like the Hydra 70, the CRV-7 is unguided and spin stabilized. This nozzle assembly attaches to the rear of the motor and has 3 curved spring-loaded aluminum fins. Ordinarily, these are held flush to the motor case by this shear pin ring, which on loading is sandwiched between the rear bulkhead and the rear cover of the launcher. On firing, the thrust of the rocket shears the pins, leaving the ring behind and allowing the fins to spring open as the rocket clears the launcher. These fins impart a stabilizing spin of 35 revolutions per second. However, it takes some time for them to deploy, deploy, time in which the rocket could potentially drift out of alignment. So the nozzle lining, which is made out of a composite material that chars or ablates to cool the nozzle, features these canted ribs, which divert the rocket exhaust to impart a stabilizing spin during the period between motor ignition and fin deployment. This system was originally developed for the Hydra 70, which in turn was developed from the Mark 40 FFAR, which had straight radial fins which folded rearward over the nozzle compartment, and 4 rocket venturi. Now, Bristol was able to use the exact same Mark 66 motor casing as the Hydra 70, but had to change the design of the nozzle. See, the Mark 66 was originally designed to use traditional double and triple base propellants, which burn relatively coolly, and thus it could use a steel-throated nozzle. This was unsuitable to the much hotter burning Bristol propellant, and so Bristol switched over to a composite nozzle with a graphite throat. They also found the original fins off of the Hydra 70 difficult and expensive to mass produce. They were extruded as one solid billet and then cut to length, so Bristol switched over to investment casting, which was a lot better suited to small batch production. By giving the CRV-7 a higher velocity and making various other improvements, Bristol succeeded in achieving an impressively small dispersion of only 3 milliradians, compared to 8 milliradians for the 20mm M61 Vulcan autocannon and 29 milliradians for the Hydra 70. Now, the motor ignition signal travels from the launcher through this contact ring and through a set of wires to the igniter, which is a perforated metal basket filled with small cylindrical pellets of pyrotechnic composition. Now, originally the igniter was mounted at the rear of the motor and was ejected out the nozzle by the rocket exhaust, but this was found to cause minor damage to the launching aircraft, so in the follow-up RLU 5002A/B motor, this was replaced with the head-end permanent igniter, or HEPI, which, as the name suggests, is permanently mounted at the front of the motor and is not ejected. Now, the ignition wires are ejected, but these are considered so small and lightweight that they do not pose a significant foreign object damage or FOD hazard to the firing aircraft. Now, the igniter integrates an RF filter which prevents the rocket from accidentally being set off by things like nearby radar sets, radio transmitters, or spurious electrostatic discharges. And interestingly, when I worked at Bristol for that one summer, one of my many tasks was conducting quality control on those very RF filters. Now, the propellant in the original C-14 rocket motor contained aluminum powder to increase specific impulse, but this had the side effect of producing extremely thick white aluminum oxide smoke. This wasn't a problem when the CRV-7 was launched by high-speed jets like the CF-104 or CF-18, but it wasn't suitable for use by helicopters, which are much slower and will linger in the smoke plume for longer. As a result, Bristol developed the C-15 or RLU 5002V motor, which removed the aluminum and greatly reduced the smoke, but at the cost of a slightly lower total impulse of 9.7 kilonewton seconds or 2,185 pound-force seconds. The latest versions, the C-17 and C-18, produce even less smoke, but have an even lower total impulse of 8.5 kilonewton seconds or 1,905 pound-seconds. Thanks to their more stable composite propellant, these motors can also be stored and deployed at temperatures from -54 to +71 degrees Celsius or -65 to +160 degrees Fahrenheit without significant degradation in performance. Now, to give you an idea of just how much more powerful the CRV-7 was compared to other similar rockets of the era, shortly after its introduction, Canada participated in a series of aerial marksmanship competitions held in France against other NATO air forces. And in one of these competitions, pilots had to shoot unguided, unarmed rockets at a tower. Now, the Canadian pilot fired his rockets from a relatively short range, the standard range for something like a Mark 40 FFAR or Mighty Mouse, and because the CRV-7 was so much faster, by the time it impacted the target, there was still plenty of propellant left in the motor. So on impact, this vaporized, mixed with oxygen, and deflagrated so violently that it destroyed the tower. And Canada was actually temporarily disqualified from the competition because the judges just couldn't believe that the rocket wasn't actually armed with a warhead. Now, in the wake of this rather impressive demonstration, the CRV-7 was adopted by a number of other countries, including the United States, United Kingdom, New Zealand, Australia, France, and Germany. Now, just like the Hydra 70, the CRV-7 can be fitted with a wide variety of warheads. The most common of these are the M151 and M229 high explosive point detonating, or HEPD, simple impact fused warheads containing 4.5 kilograms or 10 pounds of high explosives. There are also the M156 smoke and M257/278 illumination warheads, which generate light in the visible and infrared spectrum respectively. The RA-79 semi-armor piercing high explosive incendiary, or SAFI, which has a 7.5 1.3 kilogram or 16-pound hardened steel case with a 75-gram incendiary charge and is designed to penetrate and set fire to hardened aircraft shelters, bunkers, and ships, and the multi-purpose submunition, or MPSM, which contains 9 M73 submunitions. However, most MPSMs have been destroyed in compliance with the 2010 Convention on Cluster Munitions. Bristol also produced a number of its own specialized warheads for the CRV-7, including the WTU-4001/B and WTU-4001/B and WTU-5001A/B practice heads like this one, which contain a soft or hardened steel rod encased in a glass-reinforced nylon fairing and are designed to match the ballistics of live warheads like the M151. Now, during the weapon's development, Bristol engineers discovered that the CRV-7 has so much terminal kinetic energy that even these practice warheads were capable of penetrating the Centurion tanks being used as range targets. And so they replaced the steel rod with a tungsten one to produce an anti-armor warhead capable of penetrating the top and side armor of a Soviet T-72 tank at a range of 3,000 meters and angles up to 40 degrees. This, in turn, led to the development of the WDU-5002/B Flechette anti-tank, or FAT warhead, which contains 5 large tungsten armor-piercing flechettes. This was then followed by the WDU-500X/B General Purpose Flechette, or GPF warhead, which contains 70 much smaller tungsten flechettes for use against personnel and lightly armored vehicles. Now, unfortunately, I don't have an example of the FAT or the GPF warhead to show you, but I do have a pair of flechettes from the GPF, which I was given as a souvenir at the end of my term at Bristol, and which I featured in my previous video on the history of flechettes, link in the description. Now, as I mentioned in that video, I actually got to see one of these GPF warheads being ground tested. Now, the warhead itself comprises an inner carrier with radial slots into which these flechettes fit, and this slides into an outer sleeve fitted with a ballistic cap. Now, when the CRV-7 burns out, it sets off a little charge of a couple of grains of black powder that pushes the carrier out of the sleeve. Now, the CRV-7 at this point is rotating at 35 revolutions per second, and the centrifugal force launches the flechettes out laterally, creating this giant expanding cone of death. And to ground test this, what they did was put one of these warheads in a lathe, spin it up to 35 revolutions per second, and then fire it into a high-speed camera protected by a couple of sheets of clear plastic. I don't know if it was acrylic or polycarbonate, can't remember. And let me tell you, seeing that cone of death expanding and coming towards the camera is truly frightening. It was one of the coolest things I've ever seen. And even more frightening, even though that warhead was propelled by only a couple of grains of black powder, the carrier and its ballistic cap nearly broke through both protective panes of plastic and nearly destroyed the camera. So yeah, quite an impressive demonstration. There are 3 main launchers, or pods, used with the CRV-7, the M260 or LAU-5002 7-tube launcher, the M261 or LAU-5003 19-tube launcher, and the SUU-5003, which is used for training and holds 4 rockets and 6 practice bombs. The last major variant of the CRV-7 worth mentioning is the PG, or Precision Guided, which was introduced by Bristol in 2007 and features a special seeker head developed by Norwegian firm Kongsberg Defence and Aerospace, containing guidance fins, a simple inertial navigation system, and an optical sensor that can home in on regular laser designators or radar emitters for anti-radiation use. This allows the CRV-7 to be turned into a precision-guided munition far cheaper than conventional air-launched missiles. Now, while the CRV-7 continues to be used by the armies of the United States, Australia, and New Zealand, Canada's stockpile was declared expired and obsolete in the year 2000 and phased out by the year 2007. By 2021, there were some 83,000 rocket motors and 8,000 warheads being stored at Canadian Forces Detachment Dundurn in Saskatchewan, the province right next door to mine, awaiting disposal. However, in 2024, the Canadian government announced that it would instead be shipping most of these weapons to Ukraine as military aid in their ongoing war with Russia. Now, while Ukraine does have an air force, the majority of these CRV-7s will instead be deployed in ground or vehicle-mounted launchers as rocket artillery. And that, I think, is a pretty thorough summary of the CRV-7. And all that's left now is for me to talk about a couple of the other experiences I had while working at the facility that manufactures these, which is located in Rockwood, around 10 kilometers north of Winnipeg, near the Stony Mountain Federal Penitentiary. As you can see from this Google Maps image, the facility is built very much like an ammunition depot, with widely dispersed buildings surrounded by earthen berms so that a fire or explosion in one can't set off a chain reaction in the others. And one of the first things that struck me when I started working there was just how old everything was. All of the equipment was clunky and analog, and it really felt like working at NASA in the 1960s. I was also struck by the surprising lack of automation. Pretty much everything from laying up the insulation in motor cases to mixing and pouring and curing the propellant and every other process was either done by hand or only in a semi-automated fashion. And this sort of makes sense for things like the Black-Brown sounding rocket, which is a very expensive, low production sort of item. I think only about 1,000 of them have been launched since the 1950s, but I was surprised that these techniques were also used for the CRV-7, which is produced, of course, in much larger numbers. Though I suppose, given the reliability and the performance expected of these, hand building makes a little bit of sense. Now, in addition to giving me one of my coolest work experiences, which was seeing the demonstration of that general-purpose Flechette warhead, my time at Bristol also gave me one of my worst work experiences. See, the company had a little bit of a problem. They had accidentally mixed in some silica gel desiccant in a batch of CRV-7 propellant, and they weren't quite sure what sort of FOD hazard that those particles would pose to a launching aircraft. And so to find out, they took a test motor, clamped it down, and fired it at a huge sheet of styrofoam, which would catch anything coming out of the motor. And my thankless task was to pick through all of the styrofoam looking for these particles of silica gel. And the technique that they prescribed was to take a utility knife and cut the styrofoam into millimeter-wide slices looking for these little grains of silica gel. And I decided to try it out for a day, but it quickly became clear that this was just not going to work. This piece of styrofoam was like 3 meters by 3 meters, and to cut that into 1 millimeter wide strips was unbelievably tedious, and also it was very difficult to get consistent width and to find these particles. It was just not going to happen, at least not in the time frame they gave me. I only had about 2 weeks left in my work term. And so I asked them, hey, there must be a more convenient way of doing this. Can I just dissolve the foam in some sort of chemical and pick through it? Like, we don't know how that will affect the silica gel. This isn't the proper procedure. But eventually I convinced them that, to let me talk to the chemist who worked at the facility. And together we found out that acetone dissolved the foam and left the silica gel alone. And with a bit more persuasion and his blessing, they said, okay, go with that technique. So I thought I was home free. I would get this done really quickly. Well, I did, but that came at a price because I soon discovered that there are no lab gloves, at least none that were available in the city, that can withstand acetone for very long. They would just fall apart. And so I ended up having my hands in acetone 5 days a week for 2 weeks straight. And my God, by the end of that work term, my hands were super dry and they hurt and they were cracking. It was awful. But I got the job done much faster than I ordinarily would have, and probably a lot more accurately, since it was much easier to pick through this goo than it was to slice the foam into little slices. But the story doesn't end there, because once the process was complete, it produced a lot of this dissolved styrene goo. And the chemist and I put this into plastic bags, along with a bunch of propellant samples that were being tested, and we left this on the lab counter over the weekend, fully intending to incinerate them in the burn pit the following week. When we got back on Monday, though, we found that one of these bags had tipped over, and this goo had oozed into the lab sink and down into the drain. And it was of this absolutely fiendish consistency. It was too thick to flush out with water, and it was too thin to drain snake. And so the company had to call in a plumber at great expense to take apart all of the pipes in the laboratory and scoop all of this goop out. And thankfully, I was long gone by then. I didn't have to face the music for that particular misadventure. So yeah, those are my personal experiences working just a couple of months at the Bristol Rockwood propellant plant, but it was a fascinating experience, and yeah, one I am very glad I got to have. Anyway, that's all I have for you today. I hope you found that interesting. I certainly had fun reminiscing on old times and having a look at this hardware. Also, a huge thank you to Hair Force, my local military barbershop, for loaning me these items. They have a bunch of really cool hardware on display, some of which I've previously featured on this channel, including the helicopter Vasi unit and the Ferranti Mark 8 gyro gun sight. Links to those videos in the description. I'll see you next time, another video where we'll look at yet more fascinating weapons and other devices just like this one. Until then, I'm Jean Messier from Our Own Devices. Have a great day.